So we talked about work, and now we just finished talking about heat transfer. All right, so now let's put it all together. So we're going to talk about energy balance now. If we have a closed system, which remember that means there is no mass going in or out of our system, our energy of that system can only be changed in two ways. We got work and we have heat. That's all we got. There's no other way to change our energy for a closed system. Okay, now we also know that energy is conserved. So you probably heard about that in physics if you've taken physics. So that is going to lead us to the first law of thermodynamics. Now that first law of thermodynamics states that the energy of a closed system increases or decreases by an amount equal to the net amount of energy transferred across its boundary. Okay, so now let's put that into equation form. All right, so that's basically saying that the change in energy is going to equal the energy transferred in by heat, and then we're going to subtract the energy transferred out by work. Okay, so that's essentially our first law of thermodynamics right there. Okay, now let's put it in terms of our variables. Now we're going to call this energy balance. And we can write E2 minus E1. So this is our change in energy. That's got to equal Q, that's our heat, minus work, which is W. So now we've got this relationship with change in energy. Now if you remember, in one of the previous videos, we talked about a different equation for change in energy. Now, the change in energy has to be the same if we're talking about the same system. So that means that we can let delta E also equal to the delta E we had before, which was delta KE plus delta PE plus delta capital U. So our change in energy before was the change in kinetic energy plus the change in potential energy plus the change in internal energy. Now this delta E has to be the same as this delta E, right? They can't be different because we're talking about the same system here. That means we can combine these two equations to get delta KE plus delta PE plus delta U equals Q minus W. And this gives us what's called our energy balance equation. And this is for a closed system only. Once we got mass flowing in and out, this equation is going to get a lot longer. Okay, so closed system only. But this is our energy balance equation. So when I refer to the energy balance equation, that's the one I'm talking about. Okay, and we will refer back to this a lot, as long as we're talking about closed systems. So just so it's all in one place, let's remind ourselves what these terms are. Delta KE, that is change in kinetic energy, so that's going to be 1/2 mass times velocity 2 squared minus velocity 1 squared. Delta PE is going to be mg times the change in height. And delta U is internal energy, and that typically will come from the tables, as you will soon see. And then let's label these parts or variables. So mass is going to be m. We've got v, which is velocity. H is elevation. G is gravity. There we go. Put that where you can actually see it. Okay, so that's our equation. We are going to go back to that all the time. And that goes to goes with the first law of thermodynamics, saying energy's got to be conserved. Now, there's a time rate form of energy balance. Let's write down what that is. So this is where we have dE over dt. So the time rate of change of energy, that's going to equal Q dot minus W dot. And then if we write it in words, what that means is the time rate of change of energy within the system at time t that's going to equal the net rate at which energy is transferred in by heat at time t. And then we're going to subtract the net rate at which energy is being transferred out by work. At a time t. Okay, so that's the time rate form of energy balance. We might see this one occasionally. Typically we're going to use this one though, but this is the time rate form. Okay. Now last thing I want to talk about before we get to examples is something called a polytropic process. And we're going to talk about this because we're going to have these in quite a few of our examples. Now we've got this equation right here, our work equals the integral of pressure times the change in volume. That can be used to find the work of an idealized process. All right, this P term in the integrand, that's going to be the pressure of the entire quantity of gas, not just the pressure at the piston face. Okay, so this type of process can be described by PV raised to the nth power equals a constant. Okay, or we could have pressure times the specific volume to the power of n equals a constant. So let's write that that's specific volume. So these two equations are going to describe a polytropic process, and n is usually going to be given. So essentially this type of process, if you see that equation, that's just kind of an idealized process where you're assuming that that P is the pressure of all of the gas, not just the pressure at the piston face. Okay, so that's all it is. I just want to point out that this n here is usually going to be given to you, and if you see that, you've got an idealized process. All right, so we'll stop there with the notes and we'll pick it back up with an example next time.